Well, did you say that friction was a force? If you did, you'd be correct. Wherever there's a force, there's some factors that determine its magnitude, and of course there's a direction. Let's deal with the direction first. Check this out. If I were to step onto the climbing wall, I would do so with a purpose of raising my body up. But I want you to focus more on the foot. By pushing on the foot, my direction of motion of the foot would be to push it down. See, that's where friction has a special direction. Friction is generally directed opposite the direction of motion or the implied motion. Now, my foot isn't moving, hopefully, but the implied motion of my foot is down. That means I'm applying a force down, so friction must be acting up. Friction always is directed opposing the direction of motion or the implied motion. Now, there are two types of friction. The first one is exemplified here. This is called static friction. When my foot isn't moving and it's at rest, we call it static friction. Okay, now that you've seen the moonwalk, let's make an illustration of that action. In this case, we've got a pair of feet. No making fun of my feet here. And we have one leg that we'll call this the right leg. The right leg is actually making the general direction of the motion backwards. So it's the right leg that initiates the backward motion. Now the next foot here, we'll call that the left leg. The back foot here, the left leg, is the one that's dragging at this point. Okay, well, from this picture, we can now see the application of both kinetic and static friction. The right leg initially was at rest, and therefore, static friction is acting between the foot and the floor. Now, this object, this foot right here, was sliding. This foot was dragging across the floor, and we can see that this would be an application of kinetic friction. So we have both static and kinetic friction, and it takes both of them to make the illusion work. Now that we have identified our static and kinetic friction, let's look a bit closer at the forces. If the general direction of motion is backwards, then we know that the right leg must produce a force forward. So if I was facing this way, then I had to push forward in this direction with my right foot to push my leg backwards. And if you stand up and do that, you can see that to go backwards, you have to push your foot forwards. Now, having said that, if you are able to move backwards, then that's saying that the friction between your foot and the floor had to be enough that kept it from slipping. It had to be great enough to keep your foot from slipping. Now, friction is symbolized with a lowercase f. It is such a common force that we give it its own letter, just like weight. Weight is a force that we gave its own symbol to with a capital W. So friction is symbolized with a lowercase f. And if I am pushing my foot this way, then friction must act in a direction to oppose that motion. So it must be acting backwards. All right, cool. Now on this case right here, this foot is dragging in that direction. It's literally moving to the right. Therefore, this must be the direction of the left foot. So if this is the direction of the left foot, then the friction that's acting on it must act in a direction to oppose the direction of motion. So if the foot is actually sliding backwards, then friction must act forwards. So now you can see the orientation of all the forces needed to make the illusion of the moonwalk work. Okay, well, we've got our forces here. Oh, and you can see that with every step. This is just one step, if you will, where the right leg gets actually thrown forward a little bit, while this one seems to straighten out a little bit. So it's all a continuous motion, so all the legs are in motion at the same time. But what happens is, on the next step, this one becomes the static friction, this one becomes the kinetic friction, and these two forces flip over. All right, well, you've seen how it takes both static and kinetic to make the moonwalk work. Good question to focus on right now would be, we've seen both static and kinetic. Is one bigger than the other? That's a good question. That's a real good question. Let's look a little bit closer at our forces here. Let's start with the forces on the feet. So let me ask you a question. Which do you think is bigger? The force of the right foot, or the force of the right leg, or the force of the left leg? From our picture up here, you should be able to see that the general direction of motion is backwards. Now, we know that this force acting backwards would have a tendency to push the body forwards. And this force of the right leg is pushing forwards, which is acting for the body to go backwards. So the general direction of motion is backwards. And if these two forces, the one on the right leg must be greater than the one on the left. So the net force resulting from all of those, from those two actions, must show that the right leg is greater than the force of the left leg. Well, that adds nicely to get us started considering the forces of friction. So let's compare the force of friction of the right leg to the force of the right leg. Well, here's the key right here. Friction is static in this case. So if the foot isn't moving, then these two forces must be equal and opposite, such that there is no net force resulting in the foot accelerating. And so the friction force is equal to the pushing force. Now, looking at the left leg and its two forces, we see that this foot initially goes from a point of rest to a point in motion at some speed. So it accelerated. Well, the net force that's accelerating this foot is produced by the leg and all the leg muscles here. And the force of this leg must be greater than the force of friction, because otherwise it wouldn't overcome and this foot would be at rest. And so you can see that the left leg's net force must be greater than the force of friction at that point, the magnitude of those forces. Okay, so now that you see our forces all lined up here, you can see that the force on the left leg of friction is smaller than the force on the right leg. Now, the force on the left leg is a reflection of kinetic friction, while the force on the right leg is a reflection of static friction. And you can see from our example of the moonwalk and our kind of a logical argument, if you will, getting us down to this point, you can see that the force of friction due to static friction, the force required to keep an object at rest, is greater than the friction that acts on an object as it slides past another object. So we see that static friction is greater than kinetic friction. Well, I have another cool demonstration to show you that illustrates the fact that static friction is indeed greater than kinetic friction. So let's go check out another demonstration.